When we think about multiplication, we usually picture something really simple, right? Like 3 times 4. But what happens when the things you're multiplying actually have a direction? What happens when you try to multiply vectors? Well, it turns out the answer is way more interesting than you'd think. So let's just dive right in. How do you actually multiply 2 vectors? I mean, if you have a vector for a force and a vector for a displacement, what does it even mean to multiply them? See, it's not as simple as just multiplying their lengths. We've got to deal with their directions, and believe me, that changes everything. And here's the big twist. There isn't just one way to do it. Yeah, this is the wild part. Unlike just regular numbers, vectors have 2 totally separate, fundamentally different kinds of products. And each one tells you something completely different about how those 2 vectors are interacting with each other in the real world. So why all the complexity? Well, it's all because vectors are basically the language of physics. They described real-world interactions. And think about it. Pushing a box across the floor is a very different kind of physical action than, say, using a wrench to turn a bolt. So it makes sense that physics would need different mathematical tools for these different jobs. One type of multiplication just isn't going to cut it. Okay, so meet our 2 main players. On the one hand, we have the scalar product, which you'll usually hear called the dot product. And just like the name says, the result is a scalar, a single number. This is what we use when we're calculating things like work or energy. Then, on the other hand, you've got the vector product, or the cross product, and this one is a whole different animal. The result here is a brand new vector with its own size and its own direction. This is our go-to for things like torque or magnetic forces.
All right, let's grab our first tool from the toolbox, the dot product. I really like calling this the alignment meter because that's what it does at its core. It tells you exactly how much one vector is aligned with another.
Okay, so let's break down the formula you see here. The dot product of A and B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. And that cosine of phi part, that's the secret sauce. That's the little piece of math that makes our alignment meter work. So think about it. What happens when 2 vectors are pointing in roughly the same direction? Well, the angle between them is less than 90 degrees, and the cosine of that angle is positive. And that gives us a positive dot product. It's basically the math saying, yep, these 2 are on the same team. But here's where it gets really interesting. What happens when they're perfectly perpendicular? The angle is exactly 90 degrees, and the cosine of 90 degrees is 0. So the dot product? It's 0. Zilch. Nada. It means there is absolutely no alignment. One vector has 0 effect in the direction of the other. And what if they're pointing away from each other? Now the angle is bigger than 90 degrees, and the cosine in that range is negative. This gives you a negative dot product, which is a big red flag for misalignment. It tells you they're actively working against each other. Okay, time to switch gears and pick up our second tool. This is the cross product. And I want you to think of this one as an effect generator. It's not about measuring alignment. Nope. This one takes 2 vectors and literally generates a third vector that represents some new effect, like the turning force you got from a wrench. Now take a look at this formula. It looks kind of similar, but notice that huge change. We're using the sine of the angle now, not the cosine. And this part is absolutely critical. This formula only tells you the magnitude, the size of that new vector. It tells you how strong the effect is. But the direction, for that, we need a whole other trick. And this is where the cross product gets really, really weird and powerful. The new vector it creates is always perpendicular to both of the original vectors. Just let that sink in for a second. If you imagine vector A and vector B are drawn flat on a table, their cross product isn't pointing somewhere else on the table. It's pointing straight up at the ceiling or straight down through the floor. It creates an effect in a whole new dimension. And check out that last point. If you swap the order B cross A instead of A cross B, the direction of the new vector flips 180 degrees. It's a property we call anti-commutative, and it's a huge difference from the dot product. I know this can sound a little abstract, so let's actually try it. Go ahead, get your right hand ready. Step 1, point your fingers in the direction of that first vector, A. Step 2, curl your fingers toward the second vector, B, taking the shortest path. And step 3, your thumb is now pointing in the exact direction of the new vector, A cross B. It's a cool little physical trick to solve a 3D problem. So those angle formulas are fantastic for getting the concept, right? But in the real world and physics and engineering, we usually have our vectors already broken down into their x, y, and z components. And that's where these next formulas are super useful.
They let us do all these calculations without even needing to know the angle between the vectors.
The dot product in component form is just beautiful in its simplicity. Seriously, you just multiply the matching pieces, the x's with the x's, the y's with the y's, the z's with the z's, and then you just add those three numbers up. Boom, done. You get that one single scalar number that tells you all about their alignment.
Okay, deep breath. The cross product. I know, this one looks like a beast, but don't worry about memorizing it. Just look at the structure. You see the I hat, J hat, and K hat? Those are just the unit vectors for the x, y, and z directions. So this big formula is really just a recipe for finding the coordinates of our brand new vector in 3D space.
So what's the payoff for all this math? It's right here. This is how we connect it to the real world. When we calculate the work done on an object, we use the dot product of force and displacement. Why? Because we only care about the part of the force that's aligned with the direction of motion. But for torque, for a turning force, we use the cross product. When you use a wrench, the actual turning effect is perpendicular to both the wrench itself and the force you're applying. See? Different products for different physical realities. All right, let's bring it all home. Time for the final showdown. If you only remember one thing from this whole explainer, make it what you're about to see.
Okay, here it is. The ultimate cheat sheet. On the one side, you've got the dot product. The result is a scalar, a number. It's driven by cosine. The order doesn't matter. It's commutative. And its job is to measure alignment. Then, on the other side, you've got the cross product. The result is a whole new vector. It's all about sign. The order absolutely matters. It's anti-commutative. And its job is to measure a perpendicular effect. Two completely different tools for two completely different jobs.
You know, the source material for this explainer summed it up perfectly, and I really can't say it any better than this. The dot product is a scalar. The cross product is a vector. These are entirely different mathematical objects that have different meanings.
And that really leaves us with a pretty deep thought, doesn't it? We talk about these products like they're just tools we invented to solve problems. But what if they aren't inventions at all? What if the dot product and the cross product are just the built-in language of the universe? The language we discovered that describes the fundamental geometry of how forces actually work? It's something to think about.